Hello, this is the Particle Neural Network project for the Raspberry Pi 4. This project was designed for the Computational Physics 2 class at University at Buffalo and was related to work in Professor Salvatore Raposio's research group. The goal of this work is to develop a particle neural network toy model that uses machine learning to find anomalies in CERN's massive amount of particle collision data. The model can really go anywhere, but I'll let you guys know how we started it. So the physics background. Now here's a jet. So when a particles collide with each other in a particle accelerator, they will result in breaking down into like quarks, and these quarks will fly off in different directions, and that is what a jet is. The four momentum is what we use for this, a four vector, I mean, and three momentum and one is mass. We use natural units where C is equal to 1. So what we get is a mass and three momentum for each Cartesian coordinate. Now, due to the large amount of data at CERN, what we are looking for is to use machine learning tactics to be able to go through all this information, because CERN produces 25 gigabytes of data a second. So we need machine learning in order to go through all this data in an adequate amount of time. In this project, we created a toy model for jet data. And the goal of this work thus far is to distinguish lighter particles from heavier particles in jets. At leading order QCD, radiation from a gluon will follow an exponential distribution, while heavier quarks will have a Gaussian distribution at leading order. This is why we're going to train our neural network to be able to distinguish particles that have a Gaussian versus an exponential distribution. So right now, what the model does is it takes in a four vector of data as input, three momentum plus a mass vector, and all the data is randomly generated. The masses are generated according to either a Gaussian or a normal distribution, and or a Gaussian or an exponential distribution. And the three momentum are calculated using random theta and phi, and uniform distribution. And below is an image of the exponential distribution for the masses. And here's the normal distribution, just checking our work, making sure the inputs are what we think they are. Now, so the four factors are both for both distributions are then concatenated together and put into one big training data set. And along with that, we input into our neural network a vector that has zeros for exponential data pieces and ones for Gaussian data pieces. And one may wonder why the three momentum in the input is even there. That is because the neural network will be handed a lot of data, and it must be distinguished between which data is useful and which is not. As far as the results go, the neural network was trained on a set of 1 million data pieces, and it was tested on 1 million data pieces. And after all of that was done, this is the test results for the test data set. As we can see, it is around 3 out of 4 accuracy. However, it's better than a pure 50-50 guess, which would we get bare minimum. So it is doing better than pure guessing. However, it's not quite very accurate yet, so we're going to have to do some changes to that. This project is still in its preliminary phase, so expecting a lot more detail by the final. The ultimate goal of this specific project is still under discussion. However, these are some of the things we can do. We can reproduce the results of this paper with a simpler model. This paper right here, decorrelated jet substructure tagging using adversarial neural networks. We could also classify the type of particle based off of information from real detectors. We can add complexity, such as generating many particles which decay and where particles are distributed. We can use radiation patterns from QCD to determine lighter from heavier particles. And we can do absolutely anything else. That seems like a great idea. And here are the desktop instructions. You're going to need Jupyter, Python 3, and TensorFlow. And here are detailed Raspberry Pi 4 instructions. Now, let me show you the code. So we set P equal to 100. That's the momentum. We set our training set and our test set. Then we create the exponential and Gaussian data distributions each. And then this cell block, we concatenate them all together into a nice, neat training set, a nice, neat testing set. Here we're running the neural network. As we can see, it's claiming around 85% accuracy. This is showing the exponential distribution and normal distribution to check our work. This is for one specific data piece. As we can see, the model correctly guessed the Gaussian exponential distribution, but did so, but barely. It didn't do it quite as well as we would hope. This is the Gaussian, and it did correctly guess it as a Gaussian, but that's still heavy margin of thinking it was an exponential. For this one, it correctly guessed a Gaussian distribution by a landslide, a lot more than the other one. However, in this plot, it incorrectly guessed a Gaussian distribution for an exponential one, and it did that by a landslide. I really thought it was an exponential, but in reality, it was a Gaussian. And here are there's the printout from the wiki file. And as we can see, this is how much it correctly guessed an exponential distribution when it was one. This is when it said it was a Gaussian when it was actually an exponential. This is when it thought it was a Gaussian and it was in fact a Gaussian distribution. And this was one where it thought it was an exponential when it was a Gaussian distribution. And that's about it. See you for the final.